Imagine stepping into the grandest laboratory ever built, one that stretches across billions of light years, where the experiments are so vast they reshape galaxies, and so strange they defy the laws of physics as we know them. This isn't a human invention, it's the universe itself, silently conducting trial after trial in the cosmic dark, pushing matter, energy, and even time to their absolute limits. For millennia, we've gazed at the stars, thinking we were mere observers. But what if we've been watching something far more extraordinary? What if the cosmos isn't just a static stage but an active, relentless scientist, running experiments so colossal and bizarre they challenge everything we thought we knew? Take a moment to picture it: stars that vanish without warning, black holes that slow time to a crawl, and mysterious forces pulling entire galaxies toward an unseen abyss. These aren't plot twists from a sci-fi novel, they're real phenomena, unfolding right now in the depths of space. The universe doesn't need test tubes or lab coats. It has supernova for explosions, neutron stars for particle accelerators, and dark energy as its invisible hand, tweaking the very fabric of reality. And the most thrilling part, we're only just beginning to decipher the results of these cosmic trials. Today, we're diving into 25 of the universe's most jaw-dropping accidental experiments, each one a puzzle that has left scientists scratching their heads, rethinking textbooks, and sometimes just staring at the data in disbelief. Whether it's a star older than the universe itself, a void so empty it shouldn't exist, or a burst of energy brighter than 1,000 galaxies, these aren't just curiosities. They're clues hinting at secrets about how space, time, and matter truly work. So buckle up. This journey will take you to the edge of black holes, through the heart of galactic collisions, and into the eerie silence of the cosmos, where the universe's greatest experiments are still unfolding, and we've got front row seats. Imagine a signal so powerful it outshines entire galaxies, but only for a fraction of a second. Fast radio bursts, or FRB, are cosmic flashes so brief you'd blink and miss them, yet they carry enough energy to rival the sun's output for days. These radio waves race across the universe for billions of light years, arriving at Earth as fleeting, crackling whispers in our telescopes. The first FRB was discovered in 2007, buried in old data from a radio observatory in Australia, and since then we've detected hundreds more, each one a puzzle wrapped in enigma. What makes FRBs so baffling isn't just their intensity, but their randomness. They don't follow a schedule or pattern. One might erupt from a distant galaxy, then vanish without a trace, while others repeat sporadically like a cosmic drumbeat. Some even pulse with a rhythmic precision that defies natural explanations, sparking debates about whether we're witnessing the aftermath of colliding neutron stars, the death throes of black holes, or something even more extraordinary. One leading theory suggests magnetars, highly magnetic neutron stars, could be responsible, their crusts cracking under immense strain and releasing titanic bursts of energy. But then there's FRB 2020, a repeating signal from a nearby galaxy that coincided with a known magnetar's flare-up, offering the first tantalizing clue to their origins. Yet not all FRBs fit neatly into this box. Some arrive with a strange twist, their radio waves polarized in ways that suggest they've traveled through incredibly dense magnetic fields, like those near a black hole. Others appear to come from regions of space so empty they challenge our understanding of how such energetic events could occur there. And then there's the lingering question, could some FRBs be artificial? While most scientists dismiss the idea of alien transmissions, The possibility, however slim, adds a layer of intrigue to these cosmic Morse codes. What's truly remarkable is how much information these milliseconds-long bursts carry. By the time an FRB reaches us, its waves have been stretched, scattered, and imprinted with the fingerprints of all the matter they've passed through. Astronomers can decode these distortions to map the invisible, cosmic web of gas and dark matter between galaxies, turning each burst into a probe of the universe's hidden scaffolding. It's as if the universe designed these bursts as tools to test the limits of radiation, gravity, and even the structure of space-time itself. Every new detection peels back another layer of mystery, revealing just how much we still have to learn about the cosmos's most fleeting and powerful experiments. Deep in the cosmic shadows, hidden behind the thick dust lanes of our own Milky Way, lurks a gravitational enigma so powerful it's tugging hundreds of thousands of galaxies, including ours, toward an unseen destiny. This is the Great Attractor, a mysterious focal point in space where the rules of gravity seem to warp on a scale we can barely comprehend. Picture the universe as a vast, flowing river, with galaxies caught in its current, all drifting toward some invisible waterfall. That's the unsettling effect this region has on everything around it, pulling us at over 2 million kilometers per hour toward, well, we're not entirely sure what. For decades, the Great Attractor remained one of astronomy's most stubborn puzzles, simply because it lies in what's called the zone of avoidance, an area obscured by the dense gas and stars of our galaxy's disk. It wasn't until the advent of X-ray and infrared telescopes that we pierced through the cosmic fog and caught glimpses of what might be at work. What we found was both awe-inspiring and humbling, a colossal supercluster of galaxies, each with their own gravitational pull, combining to create a titanic force. The Norma cluster, as it's known, sits at the heart of this region, surrounded by sprawling filaments of dark matter and galaxies, all woven together in a web of unimaginable mass. Yet even this might not fully explain the Great Attractor's sheer power. Some scientists speculate there's something even larger lurking beyond it, and structure so massive it makes the Norma cluster look like a mere ripple in a much deeper cosmic pond. This could be the Shapley supercluster, a gathering of galaxies over 4 times more massive than the Great Attractor, lying even farther away but exerting its own gravitational influence. It's as if the universe is playing a game of nested dolls, with each layer revealing a more mind-bending scale of structure. What makes this experiment so fascinating isn't just the scale of the forces at play, but what it reveals about the invisible scaffolding of the cosmos. Dark matter, the mysterious, unseen substance that makes up most of the universe's mass, is thought to be the hidden hand behind these gravitational currents. The Great Attractor could be a laboratory for testing how dark matter shapes the universe, warping space into valleys and peaks that guide the motion of galaxies like marbles rolling across a bent sheet. And then there's the unsettling question, where is this river of galaxies ultimately taking us? While the pull of the Great Attractor is undeniable, it's not the end of the journey. The Milky Way, along with countless other galaxies, is part of an even larger flow, the Laniakea supercluster, a vast cosmic watershed where galaxies stream toward shared gravitational basins. It's a reminder that we're not just observers of the universe's experiments, we're active participants, caught in a celestial dance choreographed by forces we're only beginning to map. The Great Attractor may be hidden from our view, but its influence is undeniable, a cosmic conductor orchestrating the motion of galaxies on a scale that stretches the limits of our imagination. Imagine a hole in the universe so vast you could drop our entire Milky Way galaxy into it, and it would barely make a dent. The Boötes Void isn't just empty space, It's a staggering cosmic desert spanning 330 million light-years, where the usual shimmer of galaxies is replaced by an eerie, almost unnatural darkness. Astronomers call it the Great Nothing, and for good reason. Where most regions of the universe teem with thousands of galaxies, this void contains only a few dozen scattered like lonely islands in an endless sea. How does something this empty even exist? The answer might lie in a cosmic game of billiards played billions of years ago. One leading theory suggests that smaller voids, like bubbles in foam, merged over time, their edges collapsing until they formed this incomprehensible expanse. Another possibility is that an ancient catastrophic event, perhaps a collision between universes in a multiverse scenario, scooped out matter like a spoon carving through cosmic jelly. But the most unsettling idea, that our understanding of how matter clumps together in the universe might be fundamentally flawed. What makes the Boötes Void so fascinating isn't just its size, but what it reveals about the universe's structure. On the largest scales, matter isn't randomly scattered. It forms an intricate web of filaments and voids, like the foam on a freshly poured beer. The Boötes Void is the ultimate test of this cosmic web theory. If the universe were a soup, most of the ingredients would be clustered together, leaving vast broths of nothingness in between. This void is the largest pot of empty broth we've found, challenging us to rethink how gravity and dark energy sculpt the cosmos. The few galaxies that do call this void home are oddities themselves. Isolated from the bustling galactic cities found elsewhere, these lone starships drift through the emptiness, their shapes and behaviors warped by their solitary existence. Some appear stretched or dimmed, as if the void itself is leeching their vitality. Others might be the remnants of a once thriving community, their neighbors long since pulled away by the universe's expansion. Studying these galaxies is like finding footprints in a desert, clues to an environment so harsh it reshapes everything within it. Could the Boötes Void be the universe's way of testing the limits of emptiness? By creating a space where matter is almost entirely absent, it forces us to confront how little we truly understand about the forces that govern cosmic structure. Every observation deepens the mystery, leaving us to wonder, is this void a fluke or a sign that the universe operates on rules we've yet to comprehend? One thing is certain, the Great Nothing isn't just empty space. It's a laboratory, and the experiment is still running. Picture standing near the edge of a black hole, watching a clock tick slower and slower until it seems to freeze completely. This isn't science fiction, it's one of the universe's most mind-bending experiments, where gravity becomes so intense that time itself stretches like taffy. Einstein's theory of relativity predicted this eerie phenomenon, but it wasn't until we observed stars skirting the edges of supermassive black holes that we saw time dilation in action. Take the star S2 orbiting the Milky Way's central black hole, Sagittarius A. As it swings close to the event horizon, its light reddens and its motion appears to crawl from our perspective, as if the universe has hit the slow motion button. What's even stranger is that time doesn't just slow down uniformly. If you could hover near a black hole's edge while a friend stayed far away, they'd see your movements grind to a near halt, while for you, their actions would seem to speed up frenetically. This asymmetry isn't a glitch, it's a fundamental feature of spacetime, revealing how gravity shapes reality itself. The universe isn't just testing time's flexibility. It's showing us that time is a local phenomenon, tied irrevocably to where and how we measure it. But black holes take this experiment even further. At the event horizon, time dilation becomes so extreme that, from an outside observer's view, anything crossing it would appear to stop forever, frozen in a single moment. Yet for the unlucky object falling in, time marches on normally, a paradox that still puzzles physicists. Some theories suggest this cosmic sleight of hand might be the universe's way of hiding information, a clue to how black holes preserve or destroy it. The practical implications are just as staggering. GPS satellites orbiting Earth have to account for tiny time distortions caused by our planet's gravity, a minuscule effect compared to a black hole's grip, but proof that time dilation isn't just a far-off curiosity. It's woven into the fabric of everyday technology. The universe, it seems, is constantly tweaking the rules of time, inviting us to question whether time is even a universal constant, or just another variable in its grand laboratory. And then there's the ultimate question: what happens to time inside a black hole? Beyond the event horizon, our understanding of physics breaks down. Time might loop, reverse, or cease to have meaning altogether. The universe's experiment here is a locked box, and we're still fumbling for the key. Every observation peels back another layer, revealing just how little we know about the true nature of time and how eager the cosmos is to test its limits. One moment it's there, a pinpoint of light burning steadily in the cosmos. The next, it's gone, as if someone flipped a cosmic switch. That's exactly what happened with VVVWIT-08, a star that didn't just flicker or fade but vanished almost entirely, dimming by a staggering 97% before disappearing from view. This wasn't a supernova, the dramatic death throes of a star. It wasn't a black hole swallowing its light. It was something far more puzzling, a star that simply stepped out of sight. Astronomers first spotted this celestial magic trick using the Vista telescope in Chile, part of a survey designed to map the Milky Way's bulge. At first, they assumed it was a glitch or an error in the data. But repeated observations confirmed the impossible. A star that had been shining steadily for years had abruptly cloaked itself in near-total darkness. The leading theory, a colossal, uneven dust cloud, one so thick and vast it could eclipse the star almost completely. But here's the catch: dust clouds don't just appear overnight. They form over millennia, drifting through space like cosmic fog. For a star to vanish this suddenly, the dust would need to be moving at impossible speeds or arranged in a structure so precise it defies natural formation. Then there's the wilder possibility, the one that sends shivers down the spines of astronomers and sci-fi fans alike. Could this be evidence of alien engineering? The idea isn't as far-fetched as it sounds. In the 1960s, physicist Freeman Dyson proposed that advanced civilizations might build vast megastructures around stars to harness their energy. Think a shell of solar panels on a stellar scale. These hypothetical Dyson spheres, or Dyson swarms, could, in theory, block a star's light in irregular patterns, much like what we saw with VVVWIT-08. While most scientists caution against jumping to extraterrestrial conclusions, the sheer strangeness of this event forces us to wonder: is the universe testing how stars can be hidden, or is something or someone else at work? What makes VVVWIT-08 even more intriguing is that it's not alone. Other stars, like the infamous Tabby star, have shown similar but less extreme dips in brightness, sparking debates about cosmic megastructures for nearly a decade. Yet VVVWIT-08 stands apart, its near-total disappearance pushing the boundaries of what we thought possible. Some researchers speculate it could be a binary system, where one star is periodically eclipsed by a bizarre, disk-shaped companion. Others suggest it might be a new class of variable star, one that operates on timescales too long for us to have noticed before. But perhaps the most unsettling idea is that this isn't an anomaly at all, that the universe is littered with stars that blink in and out of view, and we're only just beginning to notice. If so, VVVWIT08 might be the first clue in a much larger cosmic puzzle, one where stars don't just live and die but perform vanishing acts on a stage we're only starting to see. The universe, it seems, loves a good mystery, and this disappearing act is one of its most baffling yet. Galaxies aren't supposed to defy the rules, at least not like this. Nestled about 65 million light-years away, NGC 1052DF2 isn't just unusual, it's an outright cosmic rebel. While most galaxies are anchored by vast halos of dark matter, the invisible glue holding them together, this one seems to float through space almost entirely without it. Picture a spinning carousel with no central pole, its horses flung outward yet somehow staying in perfect formation. That's the level of impossibility we're dealing with here. The discovery sent shockwaves through astrophysics because dark matter isn't just a minor ingredient in galactic recipes, it's the scaffolding of the universe itself. Without its gravitational pull, galaxies like our Milky Way should fly apart as they rotate, their stars scattering like marbles dropped on a hardwood floor. Yet NGC 1052DF2 spins calmly, its stars moving at a leisurely pace that defies every prediction. When researchers first measured its velocity dispersion, a way of gauging how fast stars are orbiting, they found it was so low that the galaxy shouldn't exist. It's like finding a skyscraper standing tall with no foundation, bricks held together by nothing but wishful thinking. So how did this cosmic oddity come to be? One theory suggests a violent past. Perhaps it was once a normal galaxy until a catastrophic collision stripped away its dark matter, leaving behind a ghostly skeleton of stars. Simulations show that smaller galaxies can be eaten by larger neighbors, their dark matter ripped away in the process. But NGC 1052DF2 isn't some tiny dwarf galaxy. It's sizable, with a structure too pristine to fit this brutal narrative. Another idea posits that dark matter and regular matter somehow became separated during the galaxy's formation, like oil and water refusing to mix. Yet this explanation feels more like a placeholder than an answer, highlighting just how little we understand about the rules governing cosmic evolution. The implications are staggering. If dark matter isn't essential for galaxy formation, what does that mean for our models of the universe? Could there be alternative forms of gravity at work, bending the rules in ways Einstein never anticipated? Some researchers point to modified Newtonian dynamics, or MUND, a controversial theory suggesting gravity behaves differently on cosmic scales. But even MUND struggles to explain NGC 1052DF2's extreme properties cleanly. What's clear is that the universe is conducting an experiment here, testing whether galaxies can exist outside the boundaries of our textbooks. And then there's the twist. NGC 1052DF2 isn't alone. Its sibling, NGC 1052DF4, also appears devoid of dark matter, deepening the mystery. Are these two galaxies cosmic flukes, or the first clues in a larger pattern we've yet to recognize? Every observation peels back another layer, revealing a universe far stranger and more inventive than we ever imagined. The experiment isn't over, and the results could rewrite everything we know about the invisible forces shaping the cosmos. If you thought Earth's magnetic field was strong enough to guide compasses and shield us from solar storms, prepare to have your mind stretched to cosmic extremes. Meet the Magneta, a neutron star that cranks magnetism up to levels so absurd they defy human intuition. These stellar leftovers, born from the explosive deaths of massive stars, pack the mass of our Sun into a sphere no wider than Manhattan. But what truly sets them apart isn't their density, it's their magnetic fields, which can reach a staggering 1 quadrillion times stronger than Earth's. To put that in perspective, if a magnetar hovered halfway between Earth and the Moon, its magnetic pull would erase the data from every credit card on our planet. The universe doesn't just create magnetars for show. It uses them as laboratories for testing the limits of physics. When a magnetar's crust, under unimaginable strain from those magnetic forces, suddenly cracks, it releases a starquake. These aren't gentle tremors. A single starquake can unleash more energy in 1/10 of a second than our sun radiates in 100,000 years, firing off bursts of X-rays and gamma rays detectable across the galaxy. In 2004, a magnetar 50,000 light-years away let loose a flare so powerful it briefly ionized Earth's upper atmosphere, despite being halfway across the Milky Way. But the real magic happens when you consider how magnetars warp the very fabric of reality. Their magnetic fields are so intense they actually twist space-time around them, creating a phenomenon called frame dragging. Light passing near a magnetar doesn't just bend, it spirals as if space itself has become a whirlpool. Quantum physics gets weird here too. In a magnetar's field, the vacuum of space is no longer empty. Instead, it boils with virtual particles forced into existence, a process that might even alter the star's own structure over time. Yet the most tantalizing question remains: what happens when a magnetar's magnetism crosses some unseen threshold? Some theories suggest the fields could grow so strong they temporarily freeze the neutron star's surface, creating a crystalline crust that shatters in explosive ways we've yet to witness. Others speculate that beyond a certain point, the magnetic field could collapse inward, triggering a transformation into something even stranger, perhaps a quark star or a black hole. Every flare and starquake we detect is another data point in the universe's ongoing experiment, probing how matter and energy behave under conditions we can't possibly recreate on Earth. And then there's the lingering mystery of soft gamma repeaters magnetars that fire off repeated bursts of energy at unpredictable intervals, like cosmic alarm clocks with no discernible pattern. Are these the universe's way of stress-testing magnetic fields, or is there some deeper, hidden mechanism at work? One thing's certain: magnetars remind us that the cosmos isn't just stranger than we imagine, it's stranger than we can imagine. The next time you glance at the night sky, remember, somewhere out there, a tiny, spinning powerhouse is bending the rules of reality, one magnetic field at a time. For nearly a century, gravitational waves existed only as scribbles in Einstein's equations, a mathematical prediction so subtle that even he doubted we'd ever detect them. Then, on September 14, 2015, the universe decided to show its hand. Two black holes, each about 30 times the mass of our sun, spiraled toward each other in a final, violent dance. As they merged, they unleashed a tsunami in space-time itself, sending ripples racing outward at the speed of light. By the time those waves reached Earth, they'd traveled 1.3 billion years and stretched our planet by less than the width of a proton. Yet against all odds, we caught them. The Laser Interferometer Gravitational Wave Observatory, or LIGO, didn't just confirm Einstein's theory that day, it cracked open an entirely new way of observing the cosmos. Before this, astronomy relied entirely on light, radio waves, X-rays, visible light. But gravitational waves are something fundamentally different. They're the universe's way of letting us hear collisions too dark to see, like tuning into the echoes of invisible giants crashing together in the void. That first detection was the equivalent of Galileo pointing his telescope at Jupiter's moons, a moment that rewrote the rules of exploration. Since then, LIGO and its European counterpart Virgo have detected dozens more mergers, each one revealing cosmic secrets. Some involve neutron stars slamming together, events so cataclysmic they forge gold and platinum in their wake. literally sprinkling precious metals across the universe. Others feature black holes of wildly mismatched sizes, like a cosmic David and Goliath, spinning wildly before merging into something entirely new. The data paints a picture of a universe far more violent and dynamic than we ever imagined, where collisions aren't rare accidents but part of the cosmic routine. What makes this experiment so profound is how it peels back layers of reality we never knew existed. Gravitational waves carry fingerprints of their origins, details about the objects that created them, the shape of space-time they traveled through, even clues about the universe's expansion rate. When two neutron stars merged in 2017, the event produced both gravitational waves and a gamma-ray burst, allowing us to compare these cosmic messengers for the first time. The result, they arrived within seconds of each other after traveling 130 million light-years, proving gravity and light move at the same speed, a cornerstone of relativity that had never been tested so directly. But the universe isn't done with its collision experiments. Hidden in LIGO data might be waves from phenomena we've only theorized, primordial black holes from the dawn of time, cosmic strings left over from the Big Bang, or even vibrations from higher dimensions. Some signals are so strange they defy explanation, like the potential black hole neutron star mergers that shouldn't be possible under current physics. Every detection is another puzzle piece, revealing how the universe stress tests its own laws through violent, beautiful encounters. And then there's the bigger picture. Gravitational waves might help us see the moment of the Big Bang itself. The cosmic microwave background gives us a snapshot of the universe 380,000 years after its birth, but gravitational waves could carry whispers from the first trillionth of a second, a time when space-time itself was quantum foam, bubbling with possibilities. The universe isn't just running collision experiments. It's leaving breadcrumbs through time, inviting us to trace the story back to the very beginning. In the vast cosmic tapestry, most stars are fleeting sparks burning bright for mere billions of years before fading away. But HD 140283, nicknamed the Methuselah Star, isn't just old. It's a celestial paradox, a time traveler that seems to predate the universe itself. Initial measurements pegged this faint, blue-tinged star at a jaw-dropping 16 billion years old, roughly 2 billion years older than the current estimated age of the cosmos. Even after refined calculations brought its age down to around 14.5 billion years, uncomfortably close to the universe's 13.8 billion year timeline, the mystery only deepened. How can a star exist before the stage it stands on? The Methuselah Star hangs like a cosmic question mark in the constellation Lyrae, its light taking just over 200 years to reach us a stone's throw in galactic terms. Unlike younger stars brimming with heavy elements forged in supernovae, this ancient relic is metal poor, composed almost entirely of hydrogen and helium, the primordial ingredients of the early universe. That composition is our first clue to its extreme age, but it's the star's slow, steady pulse that really tells the tale. Like counting rings in a tree trunk, astronomers measure its oscillations to estimate how long it's been burning, a technique called asteroseismology. But here's where the universe's experiment gets twisty. If the Methuselah Star truly formed before the Big Bang's afterglow faded, it forces us to confront two radical possibilities. Either our methods for dating stars are fundamentally flawed, or our understanding of the universe's birth is missing critical chapters. Some theorists suggest the star might have formed in a rare pocket of the early cosmos where conditions allowed for rapid stellar birth, like a single sprout pushing through cracks in concrete. Others propose that dark energy, the force accelerating the universe's expansion, hasn't always behaved the way we think, subtly altering our cosmic clocks. Then there's the wild card. What if the universe is older than we've calculated? The current age estimate hinges on the Hubble constant, a measure of cosmic expansion that sparked heated debates in recent years. Alternate measurements of this constant could stretch the universe's birthday back just enough to accommodate Methuselah, but at the cost of upending other pillars of cosmology. It's as if the universe left this star here deliberately, a riddle wrapped in starlight, testing whether we'll cling to old assumptions or rewrite the rules. Perhaps most tantalizing is what Methuselah implies about stellar survival. Most stars its size should have burned out eons ago, yet it persists, defying models of stellar evolution. Could its longevity hint at unknown physics in stellar cores or processes that slow nuclear fusion to a crawl? Every photon from this ancient beacon carries data not just about one star, but about the universe's earliest moments and whether we've been telling its story wrong all along. The Methuselah Star isn't just an outlier, it's a challenge, a cosmic dare to look deeper and question everything we think we know about time itself. On October 9, 2022, a wall of energy unlike anything ever recorded slammed into Earth's atmosphere. A gamma ray burst so powerful it blinded orbiting telescopes and sent scientists scrambling for explanations. Designated GRB 221009A, this cosmic detonation earned the nickname the Brightest of all time for good reason. In just 10 seconds, it unleashed more energy than our Sun will produce across its entire 10 billion-year lifespan. Even more astonishing, this explosion wasn't happening in our galactic backyard. It originated 2.4 billion light-years away, making its intensity all the more incomprehensible. What could possibly generate such unfathomable power? The leading suspect is the birth of a black hole, a supermassive star collapsing in on itself in a hypernova event so violent it funnels twin jets of plasma outward at nearly the speed of light. When one of those jets happens to point directly at Earth, we witness the full fury of a gamma-ray burst. But GRB 221009 wasn't just another stellar collapse. Its energy profile shattered previous records by a factor of 10, glowing brighter than 99.9% of all recorded bursts. For weeks afterward, its afterglow lingered across multiple wavelengths, from radio to X-rays, as if the universe was reluctant to let the spotlight fade. The Boöte didn't just break records, it exposed gaps in our understanding of high-energy physics. Gamma-ray bursts typically follow a predictable pattern, an initial flash of gamma rays followed by a fading afterglow. But this event defied expectations, producing X-ray and radio emissions that fluctuated wildly for months, as if the dying star's engine kept sputtering back to life. Some researchers speculate the black hole formed in stages, its jets wobbling like a spinning top before stabilizing. Others suggest the blast plowed through an unusually dense patch of interstellar material, creating shock waves that amplified its visible aftermath. Perhaps most intriguing is what the Boöte left behind. Most gamma-ray bursts signal the creation of a black hole, but this one might have birthed something even stranger, a magnetar, a neutron star with a magnetic field strong enough to distort atoms. If confirmed, it would mean the universe isn't just testing energy limits. It's experimenting with how extreme objects are forged in the crucible of stellar death. And then there's the eerie coincidence of timing. GRB 221009A's light had traveled for 2.4 billion years before reaching us, just as humanity's newest generation of telescopes came online. It's as if the cosmos staged this spectacular show precisely when we had the best seats in the house. Whether a cosmic fluke or a carefully orchestrated experiment, one thing's certain: the Boöte has set a new benchmark for stellar violence, and the universe is already preparing its next act. Most planets follow the rules they orbit stars, tracing predictable paths through the cosmos like obedient dancers in a celestial ballet, but not the rogue planets. These cosmic nomads drift through the galaxy untethered, untamed, and utterly alone, challenging everything we thought we knew about how worlds are born. Imagine an Earth-sized object, dark and frozen, sailing silently through interstellar space with no sun to warm it, no dawn or dusk to mark its days, just endless night stretching in every direction. These aren't theoretical constructs, they're real and they're everywhere. The discovery of rogue planets upended the traditional story of planetary formation. We used to think planets were accidental byproducts of star birth, coalescing from the leftover dust and gas swirling around newborn suns. But rogue worlds suggest the universe has other recipes for making planets violent ones. Some may have been violently ejected from their home systems during gravitational tugs of war between sibling planets, flung into the void like cosmic outcasts. Others might have formed directly from collapsing gas clouds, miniature failed stars never dense enough to ignite fusion. The sheer variety of these orphans hints at a universe experimenting wildly with planetary assembly, testing every possible way to build a world. Finding these invisible drifters is like searching for black cats in a pitch-black room. Without a host star's light to illuminate them, rogue planets are nearly undetectable unless they pass directly in front of a distant star, their gravity briefly bending the starlight like a magnifying glass. This phenomenon, called microlensing, has revealed thousands of candidates, with estimates suggesting there could be billions more lurking unseen in our galaxy alone. Some might even wander closer than we think. In 2020, astronomers spotted a potential rogue planet just 100 light-years away, a frozen vagabond drifting through our cosmic neighborhood. What's most haunting about these worlds isn't their abundance, it's their potential for life. Conventional wisdom says life needs a star's warmth, but rogue planets might harbor subterranean oceans heated by radioactive decay or tidal friction, hidden beneath miles of ice. In the eternal darkness, exotic ecosystems could thrive around hydrothermal vents, much like those in Earth's deepest trenches. Some theorists even speculate about atmospheres thick enough to trap geothermal heat, creating surface conditions bizarrely hospitable despite the absence of sunlight. The universe, it seems, isn't just testing how planets form, it's probing how far life can stretch the boundaries of survival. And then there's the lingering question, could some rogue planets be carrying life between stars? If microbial organisms could survive deep underground for eons, these wandering worlds might serve as cosmic arcs, ferrying life across interstellar space over millions of years. It's a radical idea, one that turns the galaxy from a collection of isolated systems into a vast, interconnected network, with rogue planets as the hidden bridges. Every new detection peels back another layer of mystery, revealing a cosmos far more dynamic and inventive than we ever imagined. The universe isn't just building planets around stars, it's scattering them like seeds in the wind, and we're only just beginning to grasp the harvest. The universe loves patterns, galaxies clustering like foam on a latte, voids stretching like bubbles in cosmic batter. But the Hercules Corona Borealis Great Wall doesn't just break the mold, it shatters it entirely. This mind-numbing structure, a sprawling network of galaxies 10 billion light-years across, isn't merely large. It's impossibly large, so vast it shouldn't exist under our current understanding of the cosmos. To put that in perspective, if you could teleport to one end of this wall, the other end would stretch so far into the distance that even light, the fastest thing in existence, would take twice the age of Earth just to traverse it. What makes this cosmic skyscraper so controversial isn't just its size but what it implies about the universe's design. The cosmological principle, a cornerstone of modern astronomy, states that on the largest scales, the universe should look roughly the same no matter where you're standing. No special places, no grand structures, just an even, homogeneous soup of matter. Yet here's the Hercules Corona Borealis Great Wall, a glaring exception that looms over the cosmic landscape like a mountain range in a world that's supposed to be flat. It's as if the universe sketched blueprints for a uniform expanse, then absent-mindedly doodled a colossal scribble right across the center. Discovered in 2013 by mapping gamma-ray bursts the violent death cries of massive stars, this wall isn't something you can see through a telescope. Instead, it's traced by the clustering of these bursts, like cosmic breadcrumbs marking the outlines of an invisible giant. The pattern was unmistakable, an arc of galaxies so densely packed it forms a filamentary structure wider than anything previously imagined. Some researchers argue it might not be a single continuous wall, but a chance alignment of smaller clusters, a trick of perspective like distant mountains appearing to merge on the horizon. But the statistical odds of such an alignment being random are astronomically low, leaving us with a paradox. Either our models of the universe's large-scale structure are incomplete, or we're witnessing something far stranger. One radical explanation whispers of primordial forces from the universe's infancy. In the first moments after the Big Bang, quantum fluctuations, tiny ripples in space-time, may have stretched to unimaginable scales during a period called inflation. Normally, these fluctuations seeded the galaxies and voids we see today. But what if some regions stretched too far, creating ultra-dense patches that later collapsed into mega-structures like this wall? It's like rolling dough with uneven pressure. Some areas bunch up into thick ridges while others remain smooth. The universe, in this view, might not have broken its own rules but simply pushed them to extremes we're only now beginning to glimpse. Yet the most tantalizing possibility is that the Hercules Corona Borealis Great Wall isn't alone. Other candidate structures, the Sloan Great Wall, the South Pole Wall, hint that our cosmic neighborhood might be more textured than we thought. Perhaps the cosmological principle isn't wrong, just oversimplified, like declaring Earth is smooth because you've only seen it from space. Zoom in, and continents, canyons, and mountains emerge. The universe, too, might have its own topography, its own hidden architecture waiting to be mapped. What's clear is that this wall isn't just a curiosity. It's a challenge, a cosmic gauntlet thrown down to test whether we'll cling to old assumptions or redraw the maps of reality. As telescopes grow sharper and simulations more sophisticated, the answer might not be whether the universe broke its rules, but whether we ever truly understood them in the first place. The night sky brims with possibilities, billions of stars, each potentially hosting planets where life could thrive. Given the staggering numbers, the universe should be buzzing with civilizations, their radio signals crisscrossing the cosmos like a galactic internet. Yet when we listen, all we hear is silence. This unsettling contradiction is the Fermi Paradox, a cosmic riddle that asks, if alien life is statistically inevitable, where is everybody? The universe seems to be conducting a grand experiment in solitude, leaving us to wonder whether we're the first, the last, or tragically alone. One explanation cuts deep: the Great Filter. This chilling theory suggests that somewhere between the birth of life and the emergence of spacefaring civilizations, there's an almost insurmountable barrier. Maybe simple life is common, but intelligence is a fluke, a cosmic lightning strike. Or perhaps civilizations inevitably destroy themselves upon discovering advanced technology, their cities crumbling beneath nuclear fire or runaway climate change. The terrifying implication: if the filter lies ahead of us, humanity's future could be far bleaker than we dare imagine. But the universe might be hiding its experiments in plain sight. Some argue that advanced civilizations could be so far beyond our comprehension that their signatures are invisible to our primitive instruments. Imagine ants trying to detect Wi-Fi signals. The technology is there, but entirely outside their frame of reference. Alien megastructures like Dyson spheres harvesting stellar energy might blend into the infrared glow of space, while their communications could use quantum entanglement or other physics we've yet to master. Then there's the zoo hypothesis, the idea that extraterrestrials deliberately avoid contact, observing us like wildlife in a cosmic sanctuary. It's a poetic thought, but one that raises unsettling questions. Who appointed them galactic park rangers, and what happens when humanity graduates from our planetary enclosure? The paradox deepens when you consider that even a single civilization, just a few thousand years ahead of us, could have colonized the entire galaxy by now using self-replicating probes. The fact that we see no evidence of such expansion suggests something is suppressing intelligence on a galactic scale. Perhaps the answer lies in time. Civilizations might bloom and vanish like fireflies in the night, their lifespans too brief to overlap. The universe is ancient. Humanity's radio signals have barely traveled 100 light years. We could be shouting into an empty theater, our voices arriving long after the audience has gone home. Or maybe life is rarer than we think, constrained by factors we've yet to grasp, a delicate balance of plate tectonics, moon stabilization, and galactic positioning that makes Earth a 1 in a trillion fluke. The Fermi Paradox isn't just a question, it's a mirror. How we interpret the silence says as much about us as it does about the cosmos. Are we the lonely heirs of a sterile universe, or just late to the party? Until we find proof, the experiment continues and the stars keep their secrets close. Next, we turn to a star that refuses to follow the script, its light flickering like a message we can't quite decipher. Most stars flicker gently, their light dipping by tiny fractions as planets orbit across their faces. Then there's Tabby's star, a cosmic enigma that doesn't just flicker but plunges into darkness without warning, dimming by up to 22% in chaotic, irregular patterns. Located 1,500 light-years away in the constellation Cygnus, this otherwise ordinary F-type star behaves like nothing else in the known universe. When astronomers first spotted its bizarre light patterns in data from the Kepler Space Telescope, they assumed it was a glitch, but the more they studied it, the clearer it became. The universe was conducting an experiment in stellar shadow play, and no one had the script. Theories erupted like solar flares trying to explain Tabby's star's antics. The initial guess, a swarm of comets, seemed plausible until calculations revealed it would take hundreds of thousands of them, all orbiting in perfect sync, to create such drastic dimming. Then came the wilder suggestions, fragments of a shattered planet, colossal dust clouds from recent collisions, or even a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harvest stellar energy. While the alien megastructure idea captured headlines, scientists remained skeptical. After all, extraordinary claims require extraordinary evidence, and Tabby's star seemed determined to keep its secrets. What makes this star so baffling isn't just the depth of its dimming but the sheer unpredictability. Most dimming events follow rhythmic patterns tied to orbiting bodies, but Tabby's star drops in brightness at random intervals, sometimes for days, sometimes for weeks, with no discernible rhythm. In 2017, it dimmed by 8% over just 48 hours, a plunge so steep it defied all conventional models. Then, as if to mock attempts at explanation, it brightened again, not smoothly but in jagged, uneven steps, as if some cosmic hand were adjusting a dimmer switch with no regard for physics. Recent observations have added new layers to the mystery. Spectroscopic data reveals that the star's light isn't just being blocked, it's being selectively filtered, with blue light dimming more than red. This suggests whatever's passing in front of it isn't solid but made of fine particles like dust or ice. Yet even this explanation falters under scrutiny. Dust should heat up and glow in infrared, but Tabby's star shows no such excess heat. It's as if the universe crafted a riddle where every answer only leads to more questions. Perhaps the most compelling clue lies in the star's long-term behavior. Historical data from old photographic plates shows Tabby's star has been gradually fading for over a century, dimming by nearly 15% in total. No known stellar process accounts for this slow, steady decline paired with erratic dips. Some researchers propose the star might be recovering from a recent cataclysm, a collision, a planetary engulfment, or even the dismantling of a moon system, leaving behind a chaotic debris field that occasionally eclipses its light. Others wonder if we're witnessing a rare phase of stellar evolution, one so brief and unusual it's never been documented before. Tabby's star refuses to fit neatly into any box, and that's what makes it so fascinating. It's not just challenging our models of stars, it's forcing us to reconsider how creative and how bizarre the universe's experiments can be. Whether the answer turns out to be mundane or revolutionary, one thing's certain: this star has rewritten the playbook on stellar behavior, and the universe is watching to see if we can keep up. Galaxies are often portrayed as serene islands of stars, drifting peacefully through the cosmic dark. But Andromeda, our closest galactic neighbor, is a predator, a cosmic carnivore slowly consuming everything in its path. Right now, it's tearing apart smaller galaxies, their stars stretched into shimmering streams that orbit Andromeda like the unraveled threads of a torn tapestry. These stellar graveyards, some spanning hundreds of thousands of light years, are the aftermath of galactic feasts, proof that the universe is running a long-term experiment in celestial mergers, and Andromeda is its star pupil. What makes Andromeda's behavior so fascinating isn't just its appetite, but the forensic evidence it leaves behind. Take the Triangulum galaxy, its third largest victim, currently being twisted and distorted by Andromeda's gravity. Then there's the dwarf galaxy M32, a dense, compact survivor that might be the stripped-down core of a much larger galaxy Andromeda devoured long ago. Like a cosmic archaeologist, astronomers study these stellar streams and remnants to reconstruct Andromeda's violent history, one that mirrors what will happen when it finally collides with our own Milky Way in about 4.5 billion years. But here's the twist: that impending collision isn't the apocalyptic smash-up you might imagine. Galaxies are mostly empty space, so when Andromeda and the Milky Way meet, their stars will slide past one another like two swarms of bees merging. The real drama happens in the gravitational dance between their supermassive black holes, which will spiral toward each other over eons, eventually merging in a burst of gravitational waves that will ripple across the cosmos. Meanwhile, new stars will ignite in the compressed gas clouds of the merged galaxy, painting the sky with unfamiliar constellations for whatever civilizations might witness it. Andromeda's current feeding frenzy offers a preview of this future. Its smooth, extended halo, a cloud of ancient stars and dark matter, isn't just the product of its own formation. It's a patchwork of digested galaxies, their identities erased but their material forever woven into Andromeda's structure. This process is how galaxies grow, not just through the slow accretion of gas, but through violent mergers that reshape them over billions of years. The universe isn't just testing galaxy formation here, it's stress testing it, pushing the limits of how structures evolve through destruction and rebirth. Yet the most unsettling question lingers: what if Andromeda's cannibalism is more than just a phase? Some simulations suggest that large galaxies like Andromeda eventually consume all their neighbors, becoming solitary giants in an otherwise empty galactic neighborhood. Could this be the fate of all galaxies, to grow so dominant they starve themselves of new material, their star formation sputtering out as they run out of fresh prey? The experiment is ongoing, and Andromeda is writing the playbook, one devoured galaxy at a time. As we watch Andromeda's relentless expansion, we're glimpsing the future of our own galaxy, a reminder that the cosmos isn't static but a dynamic, ever-changing arena where even the mightiest structures are locked in an endless cycle of collision and transformation. The universe doesn't just build galaxies, it pits them against each other, testing what happens when gravity's slow, inevitable pull brings them together. Next, we venture into a realm where matter itself defies logic, crushed into states so extreme they rewrite the rules of physics. Take a single sugar cube's worth of neutron star material, and you'd be holding the weight of Mount Everest compressed into a space smaller than a raindrop. These cosmic leftovers, forged in the fiery deaths of massive stars, are nature's ultimate pressure cookers, crushing matter into states so bizarre they defy textbook physics. At their cores, protons and electrons are squeezed together so violently they merge into neutrons, creating a superfluid so dense it vibrates like gelatin, only 1 trillion times more rigid. But the universe isn't satisfied with just neutron soup. It's using these stars as laboratories to test how matter behaves when the rules are pushed past breaking point. One of the most tantalizing mysteries is what lurks at the very center of a neutron star. As you descend through its crust, a crystalline lattice of iron nuclei so tightly packed they form a metal harder than diamond, you'd encounter a quantum sea of free-floating neutrons, their chaotic motions generating immense heat and magnetic fields. But go deeper still, and things get truly strange. Some theories suggest the core might contain hyperons, exotic particles where quarks, the building blocks of protons and neutrons, break free from their usual groupings. Others propose quark matter, a state where individual quarks mingle freely like molecules in a liquid, or even strange matter, a hypothetical substance so stable it could convert anything it touches into more of itself. The universe isn't just testing these extreme states, it's broadcasting the results. When neutron stars collide, as observed in the gravitational wave event GW 170817, they don't just create ripples in spacetime. They spew out heavier elements like gold and platinum in monumental quantities, proving these cosmic collisions are the universe's way of running particle accelerator experiments at energies we could never replicate on Earth. The aftermath of such mergers can briefly form a hypermassive neutron star, a fleeting, unstable monster that teeters on the edge of collapsing into a black hole, offering a glimpse into matter's behavior at the brink of oblivion. But neutron stars have even more tricks up their sleeves. Some, like PSRJ 0348 plus 0432, spin hundreds of times per second, so fast their surfaces move at 1/4 the speed of light. These pulsars act as cosmic lighthouses, their beams of radiation sweeping across space with precision rivaling atomic clocks, yet occasionally they hiccup. Glitches, sudden speed-ups in rotation, hint at the surreal physics within. One explanation involves neutron superfluid vortices unpinning from the star's crust like a pot of boiling water suddenly releasing steam, a phenomenon that lets us indirectly probe quantum mechanics on a macroscopic scale. Perhaps the most mind-bending possibility is that neutron stars could harbor portals to other dimensions. Their extreme gravity might warp spacetime so severely that they create quark stars, or even prion stars, objects theorized to exist only if particles are made of smaller, undiscovered components. The universe, it seems, isn't just pushing matter to its limits, it's asking what lies beyond those limits. Every pulse, every collision, every glitch is another data point in its grand experiment, challenging us to rethink how matter, energy, and even reality itself truly work. Saturn isn't just a ringed beauty, it's home to one of the solar system's most baffling puzzles. At its north pole, a colossal hexagon, wider than 2 Earths, spins with eerie precision. This isn't an artist's rendering or a trick of perspective. It's a real, 6-sided storm raging in Saturn's atmosphere, its razor-sharp edges defying everything we know about fluid dynamics. Discovered by Voyager in the 1980s and later studied in stunning detail by Cassini, this geometric marvel has endured for at least 4 decades, possibly much longer. Hurricanes on Earth dissipate in weeks. Jupiter's great red spot, while centuries old, is a chaotic oval, but Saturn's hexagon, it's a perfect polygon etched into the clouds, as if the universe drafted it with a cosmic protractor. What keeps this shape so unnervingly exact? The answer might lie in the interplay between Saturn's rapid rotation and the deep, churning layers of its atmosphere. On Earth, rotating fluids like coffee swirling in a cup tend to form circular vortices, but Saturn spins so fast, completing a day in just 10.5 hours, that its atmosphere behaves more like a viscous liquid sloshing in a spinning bowl. Laboratory experiments suggest that under the right conditions, such fluids can self-organize into polygonal shapes, with the hexagon emerging as a stable configuration. Yet even these models struggle to explain the sheer scale and longevity of Saturn's phenomenon. It's as if the planet is running its own fluid dynamics experiment, tweaking variables until nature produces a shape that shouldn't exist. Then there's the hexagon's eerie symmetry. Unlike earthly storms which meander and mutate, this structure remains locked in place, its vertices unwavering even as hurricane force winds scream through it at over 300 kilometers per hour. Inside the hexagon, smaller vortices dance like fireflies, some as large as continents, yet none disrupt the overarching geometry. Some researchers speculate that a standing wave pattern deep in Saturn's atmosphere acts like an invisible mold, shaping the hexagon from below. Others propose that the hexagon is a Rossby wave, a planetary scale ripple fed by differences in wind speed, though none of these theories fully account for its stark angles. The most tantalizing clue comes from the hexagon's seasonal behavior. As Saturn's north pole tilted toward the sun during its solstice, Cassini observed the hexagon's color shifting from blue to gold, hinting at chemical changes in its high-altitude haze. This suggests the hexagon isn't just a surface feature but a towering structure, its roots possibly extending hundreds of kilometers into the planet's depths. Could it be a window into Saturn's hidden interior, a fingerprint of dynamics we've yet to understand? One thing's certain, the hexagon isn't just a curiosity, it's a challenge. It forces us to rethink how turbulence and order coexist on planetary scales, and whether similar structures might lurk in the atmospheres of exoplanets or even in distant, turbulent stars. The universe, it seems, has a flair for geometry, and Saturn's north pole is its masterpiece. Next, we turn to a star that refuses to die, exploding again and again as if rewriting its own cosmic epitaph. Most stars die just once, a final, cataclysmic explosion that tears them apart in a blaze of glory. But IPTF-14 HLS, this cosmic anomaly, erupted in 2014 like any other supernova, then kept erupting. And erupting for 600 days, this so-called zombie star flickered between life and death, brightening and dimming 5 separate times as if hitting some celestial reset button. By the time it finally faded, it had released 10 times more energy than a typical supernova, rewriting the playbook on how stars meet their end. What makes this stellar revenant so baffling isn't just its persistence, but its contradictions. Most supernovae stem from one of two scenarios. Either a massive star collapses inward in a type Roman II explosion, or a white dwarf steals enough material to detonate in a type Ia blast. IPTF-14 HLS fit neither mold. Its temperature swung wildly, its hydrogen-rich spectrum defied expectations, and its light curve, the fingerprint of a supernova's energy release, resembled a seismograph during an earthquake. Even more perplexing, archival images revealed a potential explosion in the same spot back in 1954, suggesting this star had survived a previous supernova event unscathed. The leading theory involves a process called pulsational pair instability, where a star so massive, perhaps over 100 times the Sun's mass, becomes its own worst enemy. In its core, conditions grow so extreme that particles of light spontaneously transform into matter-antimatter pairs, robbing the star of internal pressure. This triggers a series of violent contractions and eruptions, each one ejecting layers of the star's outer shell while leaving the core intact. It's like a cosmic Russian nesting doll, with explosions peeling away layers until nothing remains. Yet even this explanation struggles to account for IPTF-14 HLS's extreme longevity and energy output. Then there's the wildcard scenario, a magnetar-powered supernova. If the collapsing star left behind a rapidly spinning, ultramagnetic neutron star, its rotational energy could have injected fresh power into the expanding debris, essentially re-energizing the explosion like a battery hooked up to a dying light bulb. But magnetars typically channel their energy into narrow beams, while IPTF-14 HLS's glow was spherical, another mismatch in an already confounding case. Perhaps the most unsettling implication is that IPTF-14 HLS might not be unique. Older surveys have hinted at similar prolonged supernova buried in decades-old data, suggesting the universe has been quietly running these extreme stellar endurance tests all along. Each one forces us to reconsider the boundaries of stellar physics. How massive can a star truly grow? How many times can it cheat death? And what other explosive surprises are lurking in the cosmos, waiting to upend our models? This zombie star isn't just a curiosity, it's a challenge, a cosmic dare to rethink how stars live, die, and occasionally refuse to stay dead. The universe, it seems, has more ways to destroy a star than we ever imagined, and IPTF-14 HLS is just the first clue in what might be a much larger, darker stellar graveyard. Next, we journey to a galaxy that shouldn't exist, a place where the universe seems to have ignored its own recipe for cosmic structure. Just when astronomers thought NGC 1052DF2 was a cosmic fluke, along came its enigmatic twin NGC 1052DF4. This ghostly galaxy, floating 65 million light-years away in the same galactic neighborhood, also appears to lack dark matter, the invisible scaffolding thought essential for holding galaxies together. If one dark matter-free galaxy was a puzzle, two is a full-blown cosmic conspiracy, forcing scientists to question whether they've misunderstood the universe's building blocks entirely. What makes DF4 so unsettling isn't just its missing dark matter, it's how perfectly ordinary it seems otherwise. Most galaxies without dark matter would be expected to fly apart, their stars scattering like leaves in a hurricane. Yet DF4 spins calmly, its stars moving at a leisurely pace that, by all known physics, shouldn't be possible. When researchers measured its velocity dispersion, a way of gauging stellar motion, they found it was even lower than DF2's, deepening the mystery. It's as if the universe crafted two nearly identical cosmic rebels just to see if we'd notice the pattern. The leading theory: these galaxies might be victims of cosmic theft. Some simulations suggest they were once normal galaxies until a larger neighbor, perhaps the elliptical galaxy NGC 1052, stripped away their dark matter in a slow-motion gravitational heist. Picture a galactic pickpocket so subtle it takes billions of years. As DF4 and DF2 orbited their massive neighbor, tidal forces could have peeled away their dark matter halos like husks from corn, leaving behind only visible stars. Yet even this explanation has holes. Both galaxies show remarkably symmetric, undisturbed structures, unlikely outcomes if they'd endured such violent encounters. Then there's the radical alternative. What if dark matter isn't what we think it is? Modified Newtonian dynamics, or MUND, proposes that gravity behaves differently on cosmic scales, eliminating the need for dark matter altogether. While MUND can explain some anomalies in galaxy rotation, it struggles with extreme cases like DF4, where conventional gravity fails spectacularly. Other theorists suggest dark matter might interact with itself in unexpected ways, clumping separately from visible matter during galaxy formation, a cosmic sorting mechanism we've yet to comprehend. The implications ripple far beyond these two galaxies. If dark matter isn't the universal glue we believed, entire chapters of cosmology might need rewriting. Current models rely on dark matter to explain everything from the universe's large-scale structure to the bending of light around galaxy clusters. Without it, we're left staring at a cosmic jigsaw puzzle with half the pieces missing. DF4 and DF2 aren't just oddballs, they're the universe's way of stress-testing our theories, probing whether dark matter is a fundamental ingredient or just one of many possible cosmic recipes. As telescopes like JWST peer deeper into these enigmatic systems, they're uncovering more questions than answers. Does DF4 contain trace dark matter we can't yet detect, or is it the flagship of an entirely new class of galaxies, born through processes we've yet to imagine? Every observation peels back another layer, revealing a cosmos far more inventive and far less predictable than our textbooks ever suggested. The experiment is far from over, and the universe is still writing the rules. For nearly a century after Einstein's equations first hinted at the possibility, astronomers assumed the universe's expansion was slowing down, a natural consequence of gravity pulling galaxies together like cosmic brakes. Then in 1998, two independent teams studying distant supernova dropped a bombshell. Not only was the universe still expanding, it was doing so faster and faster with each passing moment. This discovery, which won the Nobel Prize in 2011, revealed the universe wasn't just coasting, it was pressing the accelerator pedal into the floor, driven by some mysterious force we now call dark energy. The implications are staggering. If this acceleration continues unchecked, distant galaxies will eventually recede so fast their light can never reach us, leaving future astronomers with a night sky almost empty of galaxies beyond our local group. Space itself is stretching at an ever-increasing rate, as if the universe is conducting a long-term stress test to see how far it can push the fabric of reality before something breaks. Current measurements suggest dark energy makes up about 68% of the universe's total energy budget, more than twice the combined contribution of all matter, both visible and dark. Yet despite its dominance, we have no idea what it actually is. Some theories frame dark energy as a property of space itself, Einstein's cosmological constant, a form of vacuum energy that doesn't dilute as the universe expands. Others propose it's a dynamic field called quintessence, evolving over time with variable strength. The most radical ideas suggest our understanding of gravity is incomplete, requiring modifications to Einstein's equations on cosmic scales. What makes this experiment so frustrating and fascinating? is that dark energy's effects only become noticeable across vast distances, making it nearly impossible to study in labs or nearby space. The universe, it seems, has designed the perfect blind test, hiding its most pervasive component in plain sight. The acceleration isn't just theoretical. We see its fingerprints in the way galaxy clusters grow more slowly than expected, their gravitational bonds struggling against dark energy's repulsive push. It's etched into the cosmic microwave background, the afterglow of the Big Bang, where slight temperature variations reveal how dark energy shaped the universe's large-scale structure. Even gravitational waves, ripples in spacetime from colliding black holes, could eventually serve as independent probes of the expansion rate, offering new ways to triangulate dark energy's properties. Yet the biggest question remains, where is this all leading? If acceleration continues, the universe could face a big rip, where even atoms are torn apart by runaway expansion. Alternatively, dark energy might weaken over time, allowing gravity to regain dominance, or it could transition into something even more exotic, triggering a new phase of cosmic evolution. The universe isn't just expanding, it's running an open-ended experiment on its own fate, and we're living through the early chapters. As telescopes like the Vera Rubin Observatory and Euclid Space Mission map billions of galaxies, they're collecting data that could finally crack the dark energy puzzle. Each new measurement peels back another layer of this cosmic onion, revealing how little we truly understand about the forces shaping reality. The universe's expansion isn't just accelerating, it's accelerating our journey into the unknown. Star clusters are supposed to be orderly retirement homes for aging suns, groups of stars born from the same gas cloud, growing old together at predictable rates. But scattered among these stellar seniors are rebellious outliers, blue stragglers, stars that burn brighter, hotter, and bluer than their peers, like teenagers crashing a senior citizen's dance. These cosmic anomalies shouldn't exist according to standard stellar evolution, yet they've been spotted in nearly every ancient cluster we've studied. The universe, it seems, has found a cheat code for stellar aging, and we're only beginning to decipher how it works. The mystery lies in their color and energy. Blue stragglers shine with the fierce blue-white glow of young, massive stars, radiating far more energy than their cooler, redder neighbors. But star clusters form in a single epoch, meaning all their stars should be roughly the same age. In theory, any massive blue stars would have burned out billions of years ago, leaving behind only slower-burning, lower-mass stars. Yet blue stragglers persist, flaunting their youthful vigor like cosmic vampires that refuse to fade. One explanation is as dramatic as it sounds: stellar cannibalism. In the crowded core of a star cluster, where stars jostle like commuters in a cosmic subway, close encounters can lead to violent mergers. Imagine two aging stars, each too faint to shine blue on their own, colliding and combining their fuel. The result is a Frankenstein's monster of a star, reignited with fresh hydrogen to burn, its outer layers mixed and rejuvenated. Hubble observations of the globular cluster NGC 6760 revealed blue stragglers with bizarre chemical signatures, their surfaces polluted by material dredged up from deep within during such collisions. It's as if the universe is stress-testing stellar fusion, asking, what happens when stars smash together and hit the reset button? But mergers aren't the only path to rebellion. Some blue stragglers might steal their youth. In binary systems, one star can siphon gas from its companion, bulking up until it crosses the threshold into blue straggler status. This stellar vampirism leaves behind a drained, withered partner while the thief blazes with stolen energy. In the cluster Messier 30, astronomers found blue stragglers orbiting white dwarfs, the ghostly cores of dead stars hinting at this predatory past. The universe isn't just experimenting with stellar collisions here, it's testing how stars evolve when they're fed by cosmic pipelines. Then there's the wild card. Could some blue stragglers be true anomalies, born from pockets of leftover gas in clusters that somehow avoided forming stars until late in the game? It's a long shot, but recent studies of the open cluster NGC 2173 revealed a handful of blue stragglers with no clear merger or binary history, suggesting the universe might have even stranger recipes for stellar rejuvenation. What makes blue stragglers more than just curiosities is what they reveal about stellar resilience. They force us to question whether stars have a single, predictable lifespan, or if the universe has built-in loopholes, ways to extend, restart, or even rewind the clock. Every cluster we survey adds new twists to the story, proving that even in the seemingly orderly cosmos, there's always room for a few rule breakers. Next, we turn to the universe's grand infrastructure project, the invisible threads weaving galaxies together in a web of dark matter and gas. The universe doesn't build galaxies at random, it weaves them into an invisible tapestry, a sprawling network of dark matter and gas so vast it makes the largest superclusters look like mere knots in the threads. This cosmic web, stretching across billions of light years, is the hidden scaffolding of reality, its filaments acting like gravitational rivers that funnel matter into dense nodes where galaxies cluster like beads on a string. Picture it as the universe's ultimate infrastructure project, an intricate highway system where the roads are made of shadow, and the traffic is the birth and movement of entire galaxies. These filaments aren't just passive pathways, they're dynamic, thrumming with energy. Supercomputer simulations reveal how dark matter, guided by its own gravity, first formed a delicate lacework of tendrils in the early universe. Ordinary matter, the gas that would eventually ignite into stars, followed these dark matter trails, pooling at intersections to ignite the first galaxies. The web isn't static, it pulses with motion, channeling gas flows so colossal they could refuel entire galaxies for billions of years. Some filaments, like the one connecting the Able 222 and Able 223 superclusters, stretch for 58 million light-years, yet contain just 10 atoms per cubic meter, so diffuse they're nearly invisible, yet massive enough to dictate the fate of galaxies. What's truly astonishing is how we've learned to map this ghostly architecture. Since the web itself doesn't emit light, astronomers use backlit quasars, the brilliant cores of distant galaxies, to trace the filaments' outlines. As quasar light passes through these threads, specific elements in the gas, like hydrogen and helium, absorb distinct wavelengths, leaving fingerprints in the light spectrum. It's like holding a flashlight behind a spiderweb and seeing the delicate strands by the shadows they cast. Recent breakthroughs with the Keck and Very Large telescopes have captured these absorption lines in stunning detail, revealing filaments dating back to when the universe was just 2 billion years old. But the cosmic web isn't just a relic, it's a living experiment. The universe seems to be testing how efficiently matter can be organized on the grandest scales. Some filaments appear too thin and elongated to survive without dark matter's glue, while others, like the Slurp strand near the Virgo cluster, show evidence of galaxies being siphoned along them like water droplets sliding down a spider's silk. There's even evidence that magnetic fields thread through these structures, potentially influencing how galaxies spin and evolve. The most tantalizing question isn't just how the web shapes galaxies, but whether it holds clues to dark matter's true nature. If dark matter particles interact with each other, even faintly, those interactions should leave subtle marks in the web structure. Experiments like the Dark Energy Spectroscopic Instrument are now scouring filaments for signs of these hidden forces, turning the cosmos into a particle physics lab larger than we could ever build on Earth. Every new map of the cosmic web peels back another layer of mystery, revealing a universe far more interconnected than we ever imagined. These filaments aren't just backstage scaffolding. They're the universe's way of stress-testing gravity, dark matter, and the very rules of structure formation. And as we trace their faint outlines across the void, we're not just charting space, we're decoding the blueprint of existence itself. Next, we'll witness how the universe bends light into impossible shapes, turning galaxies into cosmic magnifying glasses. Einstein's theory of relativity didn't just predict that gravity bends light, it turned the cosmos into the ultimate illusionist. Gravitational lensing, one of the universe's most elegant sleights of hand, occurs when massive objects like galaxy clusters warp the fabric of spacetime so severely that light passing near them doesn't travel in straight lines. Instead, it curves, bending around these cosmic weights like a car navigating a hairpin turn. The result, distant galaxies appear stretched, duplicated, or twisted into surreal arcs and rings, as if the universe itself is playing a game of funhouse mirrors with reality. Some of the most striking examples look like something from a psychedelic dream. Take galaxy cluster Able 1689, which acts like a cosmic magnifying glass, smearing and amplifying the light of galaxies behind it into glowing streaks known as Einstein arcs. Then there's the Hamilton's object, a distant quasar whose light splits into 4 identical images around an intervening galaxy, a perfect crosshair etched into the sky. These aren't just visual curiosities, they're the universe's way of stress-testing optics on scales we could never replicate in a lab. But gravitational lensing isn't just for show. It's one of astronomy's most powerful tools, turning massive clusters into natural telescopes that reveal galaxies too faint or distant to see otherwise. The Hubble Space Telescope's Frontier Fields project exploited this effect, using clusters like MAX J0717 as cosmic zoom lenses to peer deeper into space than ever before. Some of the galaxies spotted this way existed when the universe was just a few 100 million years old infants by cosmic standards, their light amplified and preserved by the universe's own lensing experiment. The phenomenon even helps us map the invisible. Since the amount of bending depends on mass, not just visible matter, lensing exposes dark matter's hidden structures. By analyzing how background light distorts, astronomers can trace the gravitational scaffolding of galaxy clusters, revealing vast halos of dark matter weaving through them like ghostly spiderwebs. Sometimes the distortions are so extreme they hint at entirely new physics, like the galaxy cluster El Gordo, whose lensing effect suggests it might be colliding with an unseen counterpart, a cosmic wreck we can only detect by the way it bends the light behind it. Perhaps the most tantalizing possibility is time-delayed lensing. When a distant object varies in brightness like a flickering quasar, its multiple lensed images don't all change at once. The light takes slightly different paths around the lens, arriving days or even years apart. By tracking these delays, astronomers can measure the universe's expansion rate with precision, turning lensed quasars into cosmic stopwatches. It's as if the universe designed a built-in calibration tool, testing whether our measurements of space and time hold up across billions of light years. Einstein might have been the first to predict this cosmic mirage, but the universe has been running the experiment for eons, bending light into impossible shapes to probe the limits of gravity, matter, and perception itself. Every warped galaxy, every stretched arc, is another clue in a puzzle that stretches from the smallest quantum scales to the vast emptiness between galaxy clusters. The cosmos isn't just showing off, it's inviting us to look deeper, to see beyond the distortion and glimpse the hidden rules written into the fabric of space-time. Next, we'll witness a star that doesn't just shine, it thrums with the steady rhythm of a cosmic metronome. Most stars shine with unwavering constancy, their light a steady beacon across the millennia. But are our Lyrae stars? They're the cosmic drummers of the galaxy, throbbing with a rhythm so precise you could set your watch by them. Named after the prototype star in the constellation Lyra, these pulsating giants brighten and dim in cycles lasting just hours, their surfaces heaving inward and outward like a celestial heartbeat. What makes them truly extraordinary isn't just their pulse, it's how the universe seems to have crafted them as perfect yardsticks for measuring the cosmos. The secret lies in their predictability. Unlike variable stars with erratic flickers, our Lyrae stars follow a strict relationship between their pulsation period and intrinsic brightness. Once astronomers calibrate this period luminosity connection, they can use these stars as standard candles, celestial landmarks whose apparent brightness reveals their distance. This method helped map the Milky Way's structure, exposing our galaxy's halo as a sprawling cloud of ancient stars orbiting far beyond the galactic disk. In the globular cluster M3 alone, over 200 Lyrae stars twinkle in synchrony, their collective rhythms acting as a cosmic sonar pinging back the cluster's distance. Yet beneath this clockwork precision lurks a puzzle. Our Lyrae stars are old, metal-poor relics from the universe's youth, yet their pulsations defy simple explanations. They operate on a mechanism called the Kappa mechanism, where trapped heat in layers of ionized helium drives the expansions and contractions. But simulations struggle to replicate the fine details. Why some Lyrae stars exhibit sudden period changes, or why a subset display bizarre Blaschko effect modulations, their pulse amplitudes wobbling over weeks or months like a spinning top losing momentum. The universe isn't just using these stars as distance markers, it's stress-testing stellar physics under extreme conditions. In the Large Magellanic Cloud, astronomers discovered Lyrae stars pulsating in multiple modes simultaneously, their light curves resembling intricate lacework of overlapping rhythms. Others, like the star KIC 5520878, pulse so brightly they briefly distort space-time around them, their gravity waves detectable as minuscule shifts in their light. These anomalies hint at layers of complexity we've barely begun to unravel. Perhaps most intriguing is how our Lyrae stars are evolving. As they age and deplete their nuclear fuel, some transition into a phase called the red clump, their pulsations slowing like a wind-up toy running down. Others in binary systems get rebooted by stealing mass from companions, their rhythms reset in a stellar version of Fountain of Youth. The cosmos seems to be asking, how many ways can a star pulse, and what happens when you push these natural clocks to their limits? Every flicker of an Lyrae star carries data, not just about distances, but about the universe's history, the distribution of dark matter, even the rate of cosmic expansion. They're more than timekeepers, they're the universe's way of fine-tuning the very concept of time itself. As telescopes like Gaia and the Vera Rubin Observatory chart millions of these pulsators, we're not just mapping space, we're decoding the rhythmic language of the cosmos, one heartbeat at a time. Black holes are cosmic vacuum cleaners, swallowing everything that crosses their event horizons. But what if the universe has a way to spit matter back out? Enter the white hole, a bizarre theoretical counterpart where the rules of black holes run in reverse. Imagine a celestial fire hose blasting energy and matter uncontrollably into space, a region where nothing can enter, only exit. These hypothetical objects aren't just science fiction. They emerge naturally from the same equations that predict black holes, as if the universe is testing whether time itself can flip directions in the cosmic laboratory. The concept hinges on Einstein's theory of general relativity, which describes spacetime as a flexible fabric warped by mass. While black holes represent one solution to these equations, a one-way street into gravitational oblivion, white holes are mathematically valid mirror images, places where matter erupts from an impassable boundary rather than vanishing into it. Some theorists suggest white holes could be the other end of black holes, connected by wormholes in a grand cosmic recycling system. Throw an apple into a black hole here, and it might shoot out of a white hole in another corner of the universe, or even another time entirely. Yet white holes come with a glaring paradox. They seem to violate the second law of thermodynamics, which dictates that entropy or disorder always increases. A white hole's explosive output would require an infinitely organized energy source, like a cosmic magician pulling endless rabbits from a hat. To resolve this, physicists speculate these objects might only exist fleetingly, popping into existence for fractions of a second before collapsing into black holes, a cosmic hiccup in spacetime's usual rules. Others propose white holes could be remnants of black holes from a previous universe, echoing through the Big Bang into our own timeline. The universe might already be dropping hints. Some astronomers argue that certain ultra-high-energy cosmic rays or mysterious gamma-ray bursts could be white hole signatures, their sudden, unexplained energy surges matching predictions of matter erupting from a singularity. Then there's the Big Bang itself. Some theories frame it as the ultimate white hole event, a singular moment where all the universe's matter and energy burst into existence from an unknowable source. But the most tantalizing idea is that white holes aren't just mathematical quirks, they're probes into the nature of time. If they exist, they'd challenge our assumptions about causality, showing the universe can run physics experiments not just in space, but backward in time. Every theoretical white hole is a question carved into the fabric of reality. Are the cosmos's rules as fixed as we think? Or is there a hidden flexibility waiting to be uncovered? As we stand at the edge of this theoretical precipice, one thing's certain: the universe's laboratory has doors that swing both ways, and we've only just begun to push them open. What if everything you see, touch, and experience, every galaxy, planet, and atom, is nothing more than an illusion, a shimmering mirage projected from the edges of reality itself? This is the radical premise of the holographic universe theory, where our three-dimensional cosmos might actually be a two-dimensional shadow play, an intricate projection encoded on some distant cosmic boundary, like a hologram etched onto a vast, unseen surface. The idea sounds like science fiction, but it emerges from serious physics, born in the unlikely intersection of black hole thermodynamics and quantum gravity. The theory traces its roots to a startling discovery about black holes. In the 1970s, physicist Jacob Bekenstein calculated that the entropy, a measure of disorder, of a black hole isn't proportional to its volume as you'd expect, but to its surface area. It's as if all the information about what fell into the black hole wasn't lost inside its depths, but was instead smeared across its event horizon like invisible ink. Decades later, string theorists like Leonard Susskind and Gerard T. Hooft took this idea further, proposing that the entire universe might operate on the same principle: a three-dimensional reality that's actually encoded on a two-dimensional surface at its boundary, like a cosmic DVD storing a 3D movie on a flat disk. If this sounds abstract, consider a hologram in your wallet. Tilt that shiny credit card strip, and a 3D image seems to float above it, yet all that information is stored on a flat, two-dimensional surface. The holographic principle suggests our universe might work the same way, with every event, every particle, every law of physics arising from quantum bits, qubits, encoded on some unimaginably distant cosmological horizon. Your morning coffee, the Andromeda galaxy, even the sensation of time passing, all could be projections of data written on the universe's outermost shell. The implications unravel the fabric of reality as we know it. Space itself might not be fundamental but emergent, an illusion created by the entangled relationships between those boundary qubits. Gravity, in this view, could be a side effect of quantum information processing, like the heat radiating from a computer's processor. Even time might lose its status as an independent dimension, reduced to a holographic aftereffect. The universe isn't just running an experiment, it's rendering one in real time, pixel by quantum pixel. Could this explain some of cosmology's deepest puzzles? The theory naturally accounts for dark energy's mysterious influence, framing it as a consequence of information storage limits on the cosmic horizon. It also offers a fresh perspective on the Big Bang, not as an explosion in space but as a moment when the universe's operating system booted up, projecting reality from an underlying code we've yet to crack. Some versions even suggest black holes are glitches in the simulation, regions where the projection falters and the underlying data becomes visible. Yet the most mind-bending possibility isn't just that the universe is a hologram, it's that this hologram might be nested inside another. If our 3D world is a projection from a 2D boundary, what's projecting it? Could there be layers upon layers of reality, each one simulating the next? It's a hall of mirrors stretching to infinity, where every answer only deepens the mystery. The universe's grand experiment might not just be testing the laws of physics. It could be probing whether reality itself is more fragile, more malleable than we ever dared imagine. From vanishing stars to cosmic voids, the universe has been conducting its own experiments long before humans ever looked up at the sky. Each of these 25 phenomena isn't just a curiosity. It's a challenge, a deliberate tweak to the laws of physics as we know them, as if the cosmos is running trial after trial to see what sticks. Think about it, magnetars bending spacetime with magnetic fields strong enough to atomize you from light years away, rogue planets drifting alone through the interstellar dark, galaxies missing the very dark matter we thought held them together. These aren't accidents, they're the universe's way of stress testing its own blueprints, pushing boundaries until the rules break, and we're lucky enough to witness the results. What's truly humbling is how much we still don't understand. For every mystery solved, like gravitational waves confirming Einstein's century-old predictions, dozens more emerge, each more baffling than the last. The universe doesn't just defy expectations, it revels in it, crafting anomalies like Tabby's star's erratic dimming or the Boötes Void's unsettling emptiness just to keep us guessing. And that's the beauty of it. Science isn't about having all the answers. It's about the thrill of the chase, the slow unraveling of secrets hidden in starlight and space-time ripples. But here's the best part, we're not just spectators. With every telescope pointed at the sky, every algorithm sifting through data, we're active participants in this grand experiment. The James Webb Space Telescope's glimpses of ancient galaxies, the Event Horizon Telescope's snapshots of black hole shadows, even amateur astronomers catching supernovae in their backyard scopes, all of us are contributing to the greatest detective story ever told. The universe leaves clues everywhere, in the flicker of a pulsar, the whisper of a radio burst, the ghostly pull of the great attractor. It's up to us to piece them together. So, which of these cosmic riddles captivates you the most? Is it the phantom tug of dark energy silently accelerating the cosmos toward an unfathomable future? Or the haunting silence of the Fermi Paradox, echoing with the unanswered question of whether we're alone? Maybe it's the holographic universe theory, turning reality itself into a cosmic illusion. Whatever it is, let's keep the conversation going. Drop your thoughts in the comments below. And don't forget to like and subscribe for more deep dives into the universe's greatest hits. The lab doors are wide open, and the next discovery could rewrite everything we know. Until then, keep looking up. The cosmos has plenty more experiments.